So I'll give you an overview of what are the design consideration and also the operational aspects for what I call resource efficient micro-irrigation system. And when I talk about resource efficiency, I don't talk only about water, but I talk also about energy, because now everything that you do with water is somehow has an implication in terms of energy, because most of the micro-irrigation are using pressurized water, and so whatever we do as an energy implication. Tomorrow there will be an interesting talk by Aryan, who's going to talk about how the energy and the power grid looks like in California, because there are some consideration to make when you scale down to your crop and to your irrigation scheduling, and how to make the energy bill less impacting on your pocket. So what I was thinking about covering today is giving you some design consideration for micro-irrigation system in general, and then talk a little bit about vineyards water and energy requirement. I prepare a couple of practical calculation example. I'm not going to go through them, but you have it in the presentation that helps quantifying the water and energy and the bill that might come from that energy that you're going to use along the irrigation season. I'm going to talk a little bit about irrigation system evaluation and what are the information that come out of this. And tomorrow in the field session, we have a practical explanation and practical illustration of how irrigation system evaluation are conducted. And if I have time, I'm going to talk about a little bit about maintenance recommendation for your micro-irrigation system. This is really general, what it takes to be resource efficient. I think I'll start with a good design, and the good design has to somehow consider a lot of aspects that are now important in California. And when I talk about good design, it has to be done by skilled people. I would suggest not to do yourself, because you do yourself and you try to save money, and then there might be some mistakes that are costly, and to recover from those mistakes, you might have some damages to your crops. But also the design, when it's accurate and good, has somehow to factor in some flexible operation of the system, because at the beginning, your system works at a certain water and energy load, and then as the crop grows, then you have to operate at under different configuration. After we get a good design for, let's say, a certified designer, then there's to be a proper installation, because there's a lot of things that might go wrong in the field after design has been completed. So an experienced installer, but also then it gives the system to you, and you have to have the best. You have to do the best use of that system. That requires regular maintenance, routine maintenance, but also from time to time some system evaluation for you to know how that system is performing, how much water is putting on your crop, because that is really what it takes to have a proper use of water and energy. Okay. And as a third component, I would say you have to have in mind a kind of a defined irrigation strategy, whether you're going to do a full irrigation, or whether you're going to do like a deficit irrigation, sustained, or regulated deficit irrigation, and whether you're going to apply the water homogeneously across your vineyards, within the vineyards, or across the different blocks, or whether you are tailoring to specific criteria, specific strategy that you might have for the different variety. Once you have that in mind, I think you need to have an accurate irrigation scheduling, and that we heard this morning about different way of measuring stuff, or different way of estimating ET, which is the water that your crop used, the actual water used. But after you get this irrigation scheduling, then you have to implement it, all right? And then you have to implement it and get a sense of how you implement it. So your system is performing at a certain level, then your schedule is being implemented as you think or not. And I'm telling you, I travel all over the state, and we do system evaluation. I travel also sometimes internationally, when we give people and farmers or vineyard managers the results of a system evaluation, it's always, oh, it can't be that. It can't be that bad. And so it's always surprising what you think you're doing with irrigation, what you really do in the field without measuring, and assuming that everything works properly. And I'll show you some of that. So the final point is you get some feedback. So you have to close the loop and get some feedback. Is the irrigation schedule that you had in mind is being implemented as you think, and that is effective or not to your grape? I don't want it to complicate things, but this is really a general approach that we're trying to push and forward. With Calabali, we're doing an irrigation training initiative statewide for 5 different commodities, and so we are somehow putting together some training module for people to follow up. Now that California is somehow having a lot of restriction in terms of water in different areas, the Central Valley, the Central Coast, and also when energy is becoming, first of all, expensive, and somehow there's some limitation also there. So the first part is related to design, the second part is related to operation and maintenance, and the third one is related to operations. We're going to cover the 2-part in this first talk, and in the afternoon I'm going to talk a little bit about operation. Okay. So first of all, what we do with irrigation, we irrigate our crop, and our crop develops its roots in soil. And so what is really important is to know that the root system of grapevine is a woody frame, and then small roots uptaking water, develop in many directions. And this means that basically the root system of grapevine mine soil deeply or horizontally, depending where it finds the water, okay, and thrive in soil with a good balance between air and water, okay. So it doesn't like saturation, it doesn't like waterlogging, and so this has also to do with soil compaction and trying to avoid also wetting too much and waiting too much until the soil gets too dry and then re-wetting too much. So in production vineyards, been found that low volume micro-irrigation is probably the best solution, because you have, as a farmer, you have the best control on water application, nutrient application, because together with water, you provide some fertilizer, some nutrients. So you have the best level of control if you use a micro-irrigation system that is well designed, well maintained. And surface and sprinkler irrigation somehow has been used a lot in the past, especially in table grapes in some wine grape production area. But at the same time, it's been associated with increased incidence of fungal disease on leaf and clusters. So it's still, there's still a lot of room for improving sprinkler irrigation and surface irrigation, but the level of control that you have on water application, nutrient application with micro-irrigation is much better. Now, there's another aspect on this, especially now that you have self-pressure compensating system. You can plant on places that probably were not suited for sprinkler irrigation and surface irrigation. So that allowed a lot of expansion in marginal soils or in sloping areas that were not probably suited for the irrigation system of the past. Now, what I would say at the design stage, the main aspects where to focus the attention are, I would say, water supply, what kind of water supply you have, and what kind of quality of water you have, but also the main important things for design is the soil, I would say, the soil type and soil variability. But also it's important to somehow get an understanding of the slope and also how that slope looks like with respect to the sun. So you get also the aspect, because the aspect may make some difference in terms of actual water use, okay? And then you get to somehow have an understanding of how your vineyard is going to be in terms of vine spacing and row orientation, and what kind of trellis system you're going to put in place, and what is going to be your projected canopy size, and what is your canopy management. All this, as we saw this morning, have an influence on the actual water use. So the second step is, once you have everything figured out, and it's not difficult, then you design your system with a certain water application rate, and with a certain amount, maximum amount of water that you apply, what we call maximum irrigation depth. So these two parameters are the main two design parameters for a proper irrigation system design, and those have to be tailored to the type of soil you have. And so those, the parameter of the soil that you want to, really understand are the infiltration rate of the soil, and then the soil water holding capacity, okay? And the third one, for a good design, you have to have a sense of when and how much is going to be your maximum crop ET, the maximum crop evapotranspiration, because that defines the capacity of your system. So how much is the container of the soil that we're going to refill? How fast we can refill is based on infiltration rate. So how much fast we can apply water is based on the soil intake rate, okay? And how much water we should apply in order to fulfill the ET requirement. As a rule of thumb, most of the irrigation systems are designed for convenience, so for minimal cost, not really for resource efficiency. And I would say the criteria that is used, you apply the peak daily ET that normally in vineyard might happen in June or July in California, or sometime early August, and design the system to deliver that peak ET, daily ET in inches within 16 to 20 hours maximum. That time, irrigation set time, is the one that allow you to have some downtime if something goes wrong, your pump goes wrong, or you got a leak, so you got 3-4 hours to do troubleshooting and repair. So we never designed system to go on a 24-hour time set. I mean, if you're smart, you should not allow that, because if you miss something, if you miss an irrigation, it's difficult. You don't have the capacity to make it up later on, or if something goes wrong in the field. So this is just a schematic of a micro-irrigation system. What we do, we normally decide the application rate, the amount of water, maximum amount of water to apply, and then we do the hydraulic calculation, we size the component of the system from downstream to upstream. Yeah, we use several equations to do that, but I'm not going to bore you to death with that. But the criteria is to define those application rate and maximum apply water, and then design all the components from downstream to upstream. So we basically calculate the friction losses and along the pipe system, and then we size the different parts in order to provide that routine capacity, but also to provide some extra capacity, for instance, when you have to do leaching, or when you have to somehow anticipate some situation where you have like a heat wave coming, and then you have to somehow refill the soil profile that got somehow depleted. But anyway, we normally tend to buffer those risky situations, and this has to be somehow factored in the design. But also we want to ensure the operational flexibility. So I remember in 2015, I was going around in California. I joined UC Davis in 2013. It was the beginning of a 4-year drought. 2015 was the peak of the drought. So what we had, I've seen people running their system in February and March for weeks in order to refill that soil profile, okay? That's water and energy pumping. And so if you don't have enough capacity in your system, then you have to run it forever in order to refill, because we were coming out from a very dry winter. So this is part of our climate. It's not happening 1 year every 20 years. It's happening much more frequently. So I think this has to be factored in your design. So increase a little bit of capacity in order to allow you to complete an irrigation in a shorter time as possible. So the flexibility of operation is one of the criteria we normally consider when we design. So for instance, during its life, the irrigation system might operate at different conditions. Sometimes you have young vines, but those vines grow over the year, and so the flow that you have to run the system for increases over time until the vines become mature. But also you have this kind of a heat spell that you want to somehow be able to prevent or minimize the damage. The blocks could be a different elevation, so especially in this area, you got a pump, a central pump, and you get an uphill area or a downhill area. So this work at different elevation, at different flow. So it's an art to balance the system in order to make your pump work within a certain range of flow rate and pressure. Also, blocks might have different emitters because the soil infiltration and soil water holding capacity are different. So you got, now it's related to the spatial variability of your property in your soil. And you can have also composite system. You got, drip irrigation system for a normal irrigation, and then, for frost protection, you have your micro sprinkler. And so those systems work with different pressure and different flow. And so everything has to be factored in the good design. But also one thing that is happening in California, especially in the Central Valley and the Central Coast, there's a progressive decline of the aquifer level. And so if we don't factor in something in the design, in a few years, our pump is not going to be able to pump that much water because the total dynamic head increases. And so we need to do a little bit of oversizing, or we need to consider how to make our system a little bit flexible. This is an example, a system that I designed in, I think it was in southern Spain. It was for almonds. We got the pump at the center, but then you have two different blocks, and so you have to somehow balance the system in order to have your pump to work efficiently. And of course, when you operate a low-lying area, then you have a certain load. When you operate a high-lying area, you get another different load. So your pump has to cover that operational flexibility. And that's not difficult, but you have to consider it from the design. If you have a pump that works only at one fixed stage, this is your critical operation. But when you operate all the other sectors, there's a lot of energy dissipation and energy waste over there because your pump only work for a certain set, okay? So as I was telling you before, the first rule of thumb is to design your application rate in inches per hour. That should be quite lower than the soil infiltration rate. That's the criteria. So the design has to be tailored to the type of soil that you have in your vineyard, all right? So what kind of infiltration rate we normally consider? Dry soil infiltrates a lot of water. After a few hours, all the pore space are occupied with water, and so that water moves much slower. So normally, what we consider what we call the basic infiltration rate, and so we design the application rate to be able to infiltrate water after a few hours at the capacity, carrying capacity of the soil. So, for instance, if we design a system, we cannot design a system on this type of soil with a micro sprinkler that applies on a normal 0.05 because the basic infiltration rate of that soil is much lower. So after a few hours, you're going to pond water. When you pond water, you're going to have a runoff. When you're going to have a runoff, your water nutrient goes to the neighbor, not to you, and so it's not beneficial to your field. Okay, this is just an example. And these are basic value of the maximum application rate of your system for different type of soil and for different type of slope. So if you increase the slope, that water has to go probably slower because the soil has to have a little bit more time to infiltrate. Okay, so this to give you just a rough example how to define the application rate. Second rule of thumb. Your maximum application rate should not exceed the water holding capacity of your soil. Otherwise, you're wasting you're wasting water, nutrient, and energy. Okay, and this is a rough indication of the different water holding capacity. I mean, the water holding capacity that is characteristic for different type of soil. Okay, so if your soil, for instance, is a coarse texture sandy soil that has a 1 inches per feet as a water holding capacity, okay, there's no point in applying, and your root system is about 3 feet, the effective rooting system. There's no point in applying 3 inches per irrigation because more than 3 inches because you're pushing that water down, and that water might go to waste, okay? So there's criteria to size the application rate. One of the things that is really very important, especially now that everything is being planted on area, they're not very homogeneous, is to assess the spatial variability of soil features. And this is pretty easy now with the tools and technology we have. So this is an example, the Veris technology or EM38 technology. So it has the cost of about $40 to $60 per acre to run this system and get a sense how your soil look like. If you have sharp differences, then you have to somehow modify your design. You cannot apply a uniform amount of water on sharply different type of soil. So this is an example of a field at Russell Ranch at Davis where we have to design a subsurface drip irrigation for, it was an experiment in alfalfa. So what we did, they said we cannot consider this soil being uniform, and so we run a spatial analysis to understand how it was varying. You see sharp difference, and then we decide to design the system based on a critical soil or on an average soil or the most prevalent soil. Then we have to tailor our criteria. But now it's easy. I mean, don't do costly mistake, not blindly go for the uniform design when your soil might have sharp differences. There's a lot of tools out there. We normally have very quick method to estimate the soil infiltration rate and the soil water holding capacity that we can use normally in the field. And we can also use those data from different type of soil to simulate after a few hours how the shape of the wet bulb is going to be. Just to give you an example, this is something that we did when I designed the subsurface drip irrigation, because I had to decide the distance between the drip tape. Okay, so if my soil doesn't push the water laterally, but it pushes water down, why should I put so distant from each other? That, for alfalfa, you need a blanket of water. Otherwise, you're going to have a lot of let's say, yield losses. Okay, this is just an example. So we normally, as I was saying, the industry normally design the system for lowest cost and for convenience. And so these are the criteria. Your maximum application rate is given by the maximum estimated ET. So this is what the plant is gonna take during the peak period. And then you have to decide some kind of irrigation frequency based on the type of soil. And we normally divide it by the efficiency in application. Okay. So here is an example. Maximum ET daily was for an area, just number 0.25 inches. This is a peak water used for a certain crop. And maximum applied water, we decided to go on 2 days frequency. So irrigate every 2 days. You can multiply 0.25 by 2 and then divide by the efficiency of your application. That comes to about 0.6 inches. This is the amount of water that system designed for lowest cost, for convenience, should apply. Okay, might be good, might not be good. But anyway, so again, the criteria is, I would say, suggests 16 to 20 hours, but the industry design 20 to 24 hours. So to apply that amount within the period of 20 to 24 hours. Okay? And your time for irrigation comes from the maximum amount of water that you have to apply divided by the application rate. So how many inches per hour? So you have inches here and inches per hour here, and at the end you have the maximum time of irrigation. What I should really point out that I want to make sure that you design your application rate in a way that is lower than the soil infiltration rate. Okay, so that's for kind of a conservative type of design. All right. Normally, as I was saying, if we design a system based on ET, we might not have the capacity to refill the soil when we want to refill the soil, or when we are short of water for some reason. Imagine your pump gets broken, and normally this happens in July or August when you're much needed, and you try to to call the pump people to come, and they're busy around in the valley. So somehow you have some delay, your soil gets depleted. So if you design based on ET, you might not have that capacity to refill your soil. Or in case of heat spell, you need to refill your soil very fast before. Now there's a good possibility to somehow forecast the heat spell, but there's no good possibility to forecast how big they are or how dangerous they are. But the timing is probably easy to forecast. So when I normally design a system, I design based on the soil, not based on ET. It's going to be a little bit more expensive, but because I increase the capacity of my design with respect to the lowest cost, but at least people can have a flexible operation. Okay, not going to go through this, but these are the parameters that normally I use. The maximum applied water is DG max, the water holding capacity, a certain MAD, what we call the management allowable depletion, and the percentage wetted area and effective root depth and efficiency of application. So those are the parameters that are combined in a soil-based type of design. When you want to know how to convert the water depth in inches into gallon per plant, here's an easy formula. So your gallons per day is gonna be given by the water depth, so inches of water multiplied by the crop spacing and multiplied by a coefficient of 0.623. And here is a table, for instance, for evapotranspiration of 0.115 and a certain planting spacing. Then you get your basically your number of gallon per plant. Okay, so it's based on the planting spacing that you have and the planting density. Here's an example, calculation example. So all in all, I consider my soil, all the design parameter, type of soil. It comes that the maximum irrigation depth for that type of soil, it comes to 0.8 inches. This is my design parameter. And when I want to transform this into a volume per plant per irrigation, it comes to 15 gallons. This is just an example for you to go through the calculation. Typical flow rate and pressure for drip and micro sprinkler. We got really a wide range of products, and those products can go from 0.5 to 30 gallons per hour. And normally the operating pressure is somehow around 20 to 35, so there's a range of operating pressure also there. So what it really counts is not the pressure that is needed for the emitter to deliver water, but your most critical part is the filter. So even if you can deliver water to the last emitter with 7 psi, but you have to push the water to the last emitter, and so you have to have clean the water with a filtering station, and then you got friction losses. Normally, the critical component is really the filtering station. Okay. And the filtering station can be even, based on the type of water quality that you have, can be a reverse flushing system, and that, dictate your pressure requirement for applying water. The most relevant system component for me are flow meters and the pressure meters, because those are the diagnostic tool. So if you have an overpressure or an under pressure, you can spot the problem easily and you can correct the problem timely, okay? And also the important component is have a good filtration. You want to separate all the problem before the water enter in the system, because then it's going to be expensive to correct them. The other component there, especially in rolling or hillside vineyard, are important is the pressure regulator. And I'll show you why. This is an example of non-pressure compensating emitters. So you can see here that in all emission device, on all type of drippers, the flow, the amount of water you deliver, is a function of the pressure. Okay? For non-pressure compensating emitters, you got even small variation of the pressure, you got big variation of the flow. So in irrigation system, you got a lot of fluctuation of the pressure. So you see here, this is a non-pressure compensating. When we go to a pressure compensating emitter, it doesn't really matter, because it takes even large pressure variation don't change the flow so much. So this is the principal pressure compensating emitter. But all the pressure compensating emitter, they work within a certain range of pressure. If your system creates a fluctuation in the pressure because of the slope or because of the much friction losses on there, so you want to stabilize that pressure so the pressure compensating emitter can work within the defined range. So I found this very, very crucial to have a good system, distribution uniformity, and we normally even can correct some situation of systems that were badly designed or they are old and not performing very well. Now, moving to the energy, how much energy we need for pressurizing water? It normally takes 1.37 water horsepower per hour per each acre feet of water per foot of lift. This is a standard number, okay? And this is the power that the pump must provide to lift 1 acre foot of water by 1 foot, okay? So now it depends on the fuel, the type of energy, the energy source that you use. For electricity, electricity can provide a certain amount of pump output. Diesel and propane can provide a different type of output at the pump. So when you crunch your number, if your pump is powered by the energy, by electricity, this is what you need. These numbers are what you need for lifting an acre feet of water per each single foot of lift. Okay, and this standard were taken by regular publication in Nebraska pumping plant performance criteria. It's accepted actually nationwide, and it gives the standard for pumping system. What do you need this for? When you plant your vineyard, you might want to get a chance of understanding how much your energy use is going to be and how much your energy bill is going to be. Now, I work a lot in the Central Valley with almond growers and pistachio growers, and I heard now that the real challenge is the energy bill, is not the water. So they normally pay about $300 to $400 per acre in terms of water, and they pay about $800 per acre of energy. And this costs double normally during the drought. So the real cost is the energy, it's not the water at this moment. And we are talking about before Sigma implementation. So when Sigma come into play, it might be a change in the situation, but we don't know. I run a calculation example for the energy use that you can follow, but I'm not going to go, for the sake of time, I'm not going to go into detail. It comes, I compare a micro-sprinkler irrigated vineyard with a drip irrigated vineyard, and I calculated the amount of gallon of diesel that is needed for the system to perform. And it comes, of course, there's a significant difference between micro-sprinkler and drip. As I mentioned to you, energy is becoming a challenge because the power grid in California is becoming greener and greener and greener. So during the daytime, there's a much more power generation that the network can handle. And that means that, the power has to be given out for safety reason quite fast. So this happens during the daytime, okay? So, if we have the possibility in terms of our soil can infiltrate water faster and can hold that water within this boundary condition, maybe we should design the system differently, not to have such a long irrigation set time, because if we do with short irrigation set time, then we can probably benefit from the time of use type of tariff or demand response type of tariff that the energy provider, the utilities are incentivizing now. So what I mean is, it's going to look like this in the future. So if you take the energy during the off-peak time of the day, then you're going to be charged with a certain low rate, and then the power rate increases over the course of the day. And this is for recharging cars, but the way the utility is going to go for is similar to this type of scale. So if we can shorten the application of that amount of water, in a few hours, then we can benefit and lower basically the energy bill. All right? And also, if we increase that, for doing that, we need to increase the capacity of our system. This is the capacity, increases a little bit your investment cost, but in the lifetime of your irrigation system, or really the real cost is the energy, is not the investment at the moment you design. The energy, the amount of money that you pay out of energy in 20 years for your crop, it's outrageous. So even increasing a little bit that capacity, increasing that cost, will be easily compensated in 1-2 years if you can benefit from energy rates. Okay? All right. How much time do I have? 10 minutes? Okay. Irrigation system evaluation. This is something that is important because you have to know how your system is performing. So I suggest every 4 or 5 years you call a specialized crew or you do it yourself. And the type of objectives is to define what is really the real application rate of your system. It was designed, imagine it was designed 10 years ago with 0.3 inches per hour. And now you want to know how much that system really applies. Because things change over time. You get clogging, you get your pump that is not performing very well, you don't have enough pressure or have too much pressure. So the irrigation system evaluation, gives you this information. The average application rate of your system, what is the system distribution uniformity, what we call DU, whether it applies water uniformly across your plants or not uniformly, and also can detect and spot problems, and diagnose problems that you can easily correct. All right? So normally, how do you do this? You call a resource conservation district or a mobile lab, and they come to your field, and they do the catch can test, and they measure the amount of water that is delivered by different dripper in different parts of your block, okay? And so I'm going to show you this. Why is it that important that we know how much water is our system applying? This is an example of a system evaluation that we did in Chile for one project that we had. So we measure the actual evapotranspiration in the vineyard, but the vineyard was somehow had different zones, but we measure in a kind of a representative zone how much water, how much ET was the system, was the vineyard taking. And so you got this yellow-purple line that is the actual ET, the amount of water, and then we measure also how much water was applied by the dripper in different type of the block. As you can see here, we got one block that was applying much more than other blocks, and another 2 blocks, they were probably a little bit higher elevation. They were applied much less. So if that ET is your target, because that vineyard was targeting yield and not quality. So they were not applying any irrigation, regulated depth irrigation. So they were trying to provide water to match ET. So one part of the area had a little bit more than the ET, and a lot of the area had much less than ET, so they had much less yield probably, right? And so what do? In order to correct this situation, if you don't do anything to the system, what you do, you increase the water application in order to bring this part up to match ET. And that means that the higher application rate delivers much more than needed. So you got ponding, you got fungi, you got a lot of... So a system distribution uniformity is important because you might, in some situation, you might lose money. This is another system that we evaluated in another part of the farm, and it was matching pretty well. It was a newly designed system with not very much problem in pressure. And you can see the growers was pretty good at matching DET in order to, so it was having kind of a uniform yield across the field. When we spot this problem in that the farm manager said, no, it's not possible. We apply very uniform. I said, can you show the data from the yield? And then you start looking at the data. I said, oh, that area gets much less. But I never understood why. This might be a reason why. Also, together with water, you apply nutrient and fertilizer in a very different way, right? So the parameters that are normally measured in the field when people come, the crew come and do system evaluation, are flow rate and pressure in different parts of the system, the critical part, the closest part. And so there's criteria in deciding where to measure all this stuff, and you'll see during the field session. And then they calculate a distribution uniformity. And distribution uniformity is calculated dividing the average flow of your low quarter application versus the average flow. So for instance, imagine that we decide to take measurement of 16 different emitters sparse into the block, and those are the flow rate that we measure with the catch can at different emitter. And so we take the 25% of the emitters, of the total number of emitters that perform lower, and those are basically this 4, and we calculate the average of this 4 versus the average of all emitter that we measure, and it comes that basically the average flow rate of the lowest 4 emitters are 0.87, and we divide it by the total average flow rate of the other one, and we got a distribution uniformity, and in that case was 90%. That's pretty good, That means that your plant are receiving pretty similar amount of water and nutrient because, you do fertigation. This is an example of a report that you get from the irrigation system evaluation. You get average flow rate of the emitters they measure, the average application rate, how many inches per hour your system really applies, and this is the DU, and then they score your system based on certain categories. In that case, was performing very well. But also you got some other information that can give you an idea where the problems are. Let's say hose inlet pressure variation is a significant problem. Possible causes of hose inlet pressure, lack of pressure regulation, and blah, blah, blah. So you get also a sense of what are the problems that the crew notice in your field and how to correct them. And one of the most typical cause of a poor system DU is emitter clogging. You get all kind of, because you're doing fertigation, you're using a lot of, amendment through the irrigation system. So you got clogging, and the clogging could be caused by suspended material in the water, or chemical precipitation when you do fertigation, or biological growth because the bacteria can grow into the pipe because of the heat of the pipe, and root intrusion, soil ingestion. Those are the most typical causes that you have. How long do I have? 5 minutes? All right. So here is the type of clogging that can be managed through irrigation, through injection of chemical, and this is just general guidelines. This is the type of problem that you're going to correct with chlorine. You got this in the presentation, so I will not go through this. But some recommendation that I think are useful here is you have to have a professional evaluation by irrigation system evaluation every 2-3 years, especially if your crop is valuable, like in this case. Okay, if your crop generates quite a bit of income, then it's important that you know how much water is applied by your system, and because the system evaluation will be able to give you, important parameter on how to schedule irrigation. And you have to monitor the system periodically, especially in terms of pressure and flow rate. And the last thing that I want to point out, that all this is available, especially the irrigation system maintenance, in a publication that UCNR released a few years ago. It's very comprehensive. I find it very practical and useful. So it's a good source of information on how to keep your system operational. Finally, we just completed a round of evaluation for the SWEEP program, and there was another type of incentive in terms of energy, financial incentive for energy efficiency. So This round is completed, but SWEEP is going to come back, so it's going to have another round of funding available for growers and farm managers in order to upgrade the irrigation system and make it more resource efficient. So stay tuned and ask your local farm advisor here or ask Han. And all right, I'm going to stop here. Thank you for your attention.